In this work, we explore barriers to the detection of behaviors with wearable devices through the story of our effort to develop an eating detection system across 4 studies. Why are we interested in applying wearables to behavioral medicine? Without wearables, healthcare providers have no direct knowledge of a patient's life between visits. To assess lifestyle, they use self-report and memory recall, which are known to suffer reliability issues. With wearables, the patient's life between visits becomes known to the provider in the form of objective and quantitative reports that can be used to inform treatment decisions. The potential of this idea has been demonstrated on small scales. Systems have shown promise in monitoring eating, sleeping, and mental health. Despite these successes, clinical adoption of these devices remains to be seen. Barriers to clinical translation include sample selection. mHealth systems target clinical indications, and so they must be tested on representative samples rather than convenience samples if the results are to be trusted by clinicians. Another barrier is transdisciplinarity. Building an mHealth system is logistically complex and requires a team of diverse skill sets that must be united under a common purpose. Another barrier is the realism of test conditions. Lab studies are known to fail to replicate in real-world scenarios. Error can also result from other unrealistic conditions such as unrepresentative samples. Simple behaviors can often be detected monomodally. A physical jolt recorded by an inertial sensor can be used to detect a step, as is the case with pedometers. Complex behaviors such as eating require multimodal approaches. For example, a combined data stream of body gyroscopy, jaw movement, ambient light collected by an array of sensors can be used to detect eating. This is to say, we use a compositional definition of eating, which understands eating as the amalgam of several smaller behaviors: chewing, biting, leaning, and feeding gestures. To develop our eating detection system, we conducted 4 studies, 2 in the lab and 2 in the wild. For each study, we performed system development, human subjects testing, and analysis and inference of the data. In study 1, a piezoelectric pendant, which encodes force exerted upon it as electrical charge, was used to detect swallows with an F-score of 87%. In the second study, we redesigned the pendant into a snug neckband fitted with an accelerometer that provided additional information that allowed us to rule out confounding behaviors and make the system more generalizable between participants and to real-world settings. In the third study, the first in-wild study, we deployed a multimodal necklace on participants in free-living conditions. This device used an infrared proximity sensor, an ambient light sensor, and an inertial sensor to detect chews, bites, gestures, and leans respectively, with an F-score of 77%. To provide the ground truth needed to evaluate this system, participants also wore a shoulder-mounted camera and microphone aimed across the torso. In the fourth study, we used a looser necklace band to increase comfort, redesigned the camera to sit on the chest and to not include audio to decrease privacy concerns, and to use ecological momentary assessment to measure calorie intake, affective state, and context of each meal captured, providing a richer data set that may open the door for more sophisticated measurements of eating behavior down the line. We include in the paper the most important lessons learned throughout these projects, organized by project role. For hardware engineers, the most critical considerations concerned hardware testing, firmware testing, endurance testing, and the need to simulate extreme test conditions. For software and machine learning engineers, lessons primarily concerned software design, challenges involving in-lab data collection, as well as in-wild data collection, and considerations for the data annotation and labeling processes. For mechanical engineers and designers, the key lessons relate to issues of device form factor and user comfort. For research coordinators, we provide lessons related to subject recruitment, technology teaching of participants, in-field study monitoring, and Hawthorne effects introduced by observing participant behaviors. By interviewing team members, we derive 5 key axioms of developing wearable behavior detection systems. Single modality approaches often do not cut it when it comes to complex detection problems. As necessary as it might seem in the moment, The savings of cutting corners on hardware development is never worth the cost of data loss and device failures down the line. You cannot out-engineer the wild, which is to say you can only learn from it by deploying systems into the real world. Just because you think a given sensor stream will encode a desired behavior does not mean that it will. This ought to be validated before serious investment is made in wearables research. There can be cultural divides between the different specialists needed to complete an mHealth project. Encouraging teamwork and establishing norms can help unite these different professionals under a common goal. A detailed summaries of the lessons we learned across these studies, categorized by the role that would most benefit from the lessons, is provided in the paper. Thank you very much for listening to this presentation.